Alright, so here are the Unit 8 examples for section 8.3. Alright, so if we draw a circle and we make 2 points on it, the smaller arc between those two circles, so we notice that there's a point A here on the left side and a point B here on the right side. The smaller arc between A and B is at the bottom. We call that the minor arc, AB. And the bigger arc, which is at the top from A to B, that's called the major arc, AB. Alright, inscribed angles. So anytime we take an angle from 2 points of a circle and its vertex, or that very last point right at the top there, and it touches the outside of the circle, that's called an inscribed angle. And when we have an angle, I don't know if you can see my pointer, but I'm tracing over the line from A to O and then O to B, that angle there. Anytime we have an angle that's vertex is the center of the circle, or that point, that sharp point of the angle where the two lines meet, when that vertex, or where the 2 points meet, is the center of the circle, we call it a central angle. Central angle and inscribed angle property. In a circle, the measure of the central angle subtended by an arc is twice the measure of an inscribed angle subtended by the same arc. So that means if we go back here, we have an inscribed angle, A to the outside to B, and then we have A to O to B is the central angle. It means that central angle is going to be double that inscribed angle. Inscribed angle property. In a circle, all inscribed angles subtended by the same arc are congruent or equal. So if we go back to our drawing and we look at it, we have an inscribed angle. If I drew other angles that touch the outside of the circle from those 2 points A and B, they would be equal. So their measurements would, let's say it was 63 degrees, they would all be 63 degrees. Angles in a semicircle property. All inscribed angles subtended by a semicircle are right angles. So if we have 2 points at the end of the diameter, or that make 180 degrees as our central angle, our inscribed angles are going to be 90 degrees. Example 1. Find the measures of alpha and beta. Well, here we have angle ACB is equal to 55 degrees. That's what's given to us. Angle ADB is an inscribed angle with the same arc. Notice how the arc opposite of our angle is the same in AB, ACB, and ADB. That means those two angles are equal. So alpha is equal to 55 degrees. Now we have a property that tells us that inscribed angles are double or half of the central angle, so our central angle is double our inscribed angle. So beta will be 2 times ACB, or 2 times alpha. So we get 110 degrees. Don't forget your little degree circle, that little circle up here, to show that you're measuring in degrees. Because eventually in higher level maths you will be measuring in radii, which have a different unit. Example 2. ABC are vertices of a rectangle with a radius of 8.5 centimeters. The width of the rectangle is 10 centimeters. What is its length? Alright, so easiest way to do this is let's chop that guy in half. Since since we know that the radius is 8.5, the diameter is 17, and now we have a right triangle with 17 centimeters and 10 centimeters. Again, we know Pythagoras is for a right triangle, so a squared plus b squared equals c squared. We know that c squared is always our slant, and we like b to be alone. So b squared is equal to 17 squared minus 10 squared. B squared is equal to 289 minus 100. So we get b squared is equal to 189. We're looking for b because the side length is not squared, it's by itself. So we get square root of both sides. So b is roughly equal to 13.7 centimeters. That's the end of the examples for this section.